Welcome to another podcast. In this episode, we're going to be taking a look at properties of the convolution, just to sort of get you prepared for the upcoming exam. We have basically the idea behind a convolution, and we looked at or derived the formula for the convolution in class. But what we have here is the Laplace transform of, say, a function f of t and g of t. So the idea would be, if I take the Laplace transform of f of t times g of t, we would like, or we would love actually, this to be equal to the Laplace transform of f of t times the Laplace transform of g of t, which would be f of s times g of s. That's what we would love. It turns out that this isn't the case, though. So these aren't equal. Instead, so let me just put a big box around this so we know that this is not true. Instead, what it turns out to be is that I'm going to work this in reverse. Instead of f of s times g of s being f of t and g of t, it turns out that when you take the inverse transform of these, then this is equal to the inverse transform of f of s, but it's not times the inverse transform of g of s. What you end up with in this case is something called the convolution. And so one direction to remember this formula in is that the Laplace transform of f of t convolved with g of t is f of s times g of s. And the other way, or the more interesting way, is the reverse of this, which says the Laplace transform of f of s times g of s is equal to the inverse transform of f of s convolved with the inverse transform of g of s, which is f of t times g of t. F of t convolved with g of t. So the takeaway from this is these two formulas are the important ones when it comes to convolution. And so an automatic question sort of pops up here, and that is, what is f of t convolved with g of t? Now, we showed in class that if you look at the convolution, it's an integral, which we kind of expected because it's the analog of what happens with sums, and for a sum, the convolution is a sum of terms. But here, the convolution is an integral. The integral from 0 to t of whatever's first. You have a dummy variable integration, which we've used u in class, times whatever's second, you take it at the value of t minus that variable. And then the integration is with respect to u. So this is the other important formula to keep in mind here. That is that the convolution of f with g is given by this integral. So rather than having to do things like partial fractions, complete the square to be able to find the inverse transforms of products, we can instead integrate those transforms. And we can instead integrate the functions. That adds a whole different kind of problem. It's not as complex to do as partial fractions or whatnot, but doing it by hand is also not necessarily easy depending on what the functions f and g are. Taking this a step further, we talked about some properties of the convolution as well. So properties of the convolution. The first one is that the convolution is commutative, which means that f star g is the same as g star f. To see this, if you look at the integral from 0 to t of f of u g of t minus u du, I want to do a change of variables here. I want to change the variable u to be, let's see here. So I'm going to come up with a different variable here. I want to let v be equal to, let's say, t minus u. So you can see here I'm trying to turn that into a v. So if v is t minus u, then dv with respect to, let's see here, it would be dv du would be negative du. Yeah. So it would be with respect to u. So v is t minus u and dv is minus du. I'd be taking the derivative there with respect to u, or the differential with respect to u. So if I make that substitution into this integral, then the limits of integration become, well, when u is 0, v would be t, and when t is, when u is t, t minus t would be 0, so you'd get 0 here. And f of u would become f of u would be the same thing as t minus v. And g of t minus u would be the same thing as g of v. And then du would be minus dv. And what you see here is the negative here, and the fact that this limit is upside down. Remember, if I multiply through by a negative, it switches the limits of integration, and so this would be equal to the integral from 0 to t, getting rid of the negative, and then look at what you have. You just have g of v times f of t minus v. But that's the exact same thing as g star f, where the thing I began with was f star g. And so it is a commutative operation. It doesn't matter the order in which you do these things. The second part to this is what is the convolution of a function with 1? And by definition, this would be the integral from 0 to t of f of u times 1 at t minus u, but that's just 1. So it'd just be the integral from 0 to t of f of u du, which is just integration. In fact, this is called, oftentimes this is called the area function by calculus textbooks. So it's just integration. It's just the area under the curve of f. Who knew? The third one is f of t convolved with the delta function, and what this is. So this, I'm going to use the commutative property to look at delta f instead. This would be delta of u times f of t minus u du. And we use the sifting property here. So if you recall the sifting property, go back and look at a previous video. The sifting property of the delta function, which is you basically what the sifting property does is it says you take this variable and plug it in for, well, not this variable. This is, in fact, u minus 0. So you take the shift of this variable, which is the 0, and you plug it in for the variable of integration here, which is u. So this shifting property says out of all of this, what you would get is you would just get the function evaluated at t minus 0, or f of t. And so what we see here is that the delta function, it has the property that f of t convoluted with the delta function is just f of t back. That's actually a huge property. It enables us to do so many things theoretically with the delta function. So this is the fact that the delta function here is called the identity function for the convolution. These are just some of the properties that we've built up involving convolutions. In a future video, I'm going to take a look at some specific examples using the inverse transform and convolutions, as well as talk about something called Duhamel's principle, which is a way of understanding the response of any differential equation, so the response to an input based entirely off of the state of the system, entirely off the system itself. And so we'll take a look at those coming up. All right, thank you for watching.